In this video, I'm going to solve problems related to transformations of functions, compositions, inverse functions, and quadratic functions, including factoring, the quadratic formula, and the method of completing the square. We start with a problem about transformations. Use the graph of f of t shown. There's three different graphs you see here that are all f of t to graph three related functions that are transformations of the original function. G of t equals f of t minus 2. H of t equals 2 times f of t plus 1, and j of t equals negative f of t plus 1. Take them step by step. G of t is f of t minus 2. When you replace t with t minus 2 inside the parentheses for the input of f, that takes the graph of f and translates it to the right by 2 units. Why? For example, what if we wanted to find g of, let's say, 5, for example? Using this formula, we would replace t with 5, and we would evaluate f of 5 minus 2. That's f of 3. What is f of 3? You can see from this graph, it looks like it's about negative 2. It's this corresponding to this point right there on the graph. And that's going to happen for all the points. The value of g 2 units to the right of the corresponding value of f is what you're after. You want to take these points and translate them to the right by 2 units. It's good to focus on key points to help you do that. Key points include intercepts. They include, well, in this kind of graph, points where you've got corners. So here's an intercept here, here's an intercept there. You've got corners here, here, and here. You could also have a y-intercept right there. It'd be good to see where those go when I translate them to the right by 2 units. Another important point is this local maximum right there. So for example, let's start with this point here. If I translate to that to the right by 2 units, its coordinates right now are negative 2 comma positive 1. Translating it to the right by 2 units brings you to the point 0 comma 1. This point also right here would get translated from negative 3 1 to negative 1 1 right there. This point, if I translate it to the right by 2 units, will be right there. This point right here will go to that point right there. This point right here will go to that point right there. So we got to be careful here. This one will go right about there. This one will go right about here, and this one will go right about there. Now just connect those dots with the same kind of shapes that you see. A straight horizontal line there, a line going down about like this here, a little half circle kind of thing, a semicircle type of thing right here, and then a straight line going right there. So there is the graph of g of t equals f of t minus 2. It's a transformation of the graph of f to the right by 2 units, a translation. All right, part B, h of t. 2 times f of t plus 1. If I didn't have the 2 there, I would take the graph of f and shift it to the left by 1 unit, and I will do that. But now I also have to deal with the 2. The 2 is taking the outputs of f and doubling them, multiplying the second coordinates of the corresponding points by 2. So that's going to make them twice as far away from the horizontal t-axis. Their y values are twice as big, either positively or negatively. Since it's 2 steps, a horizontal translation and a vertical stretch, might be good to draw sort of like an intermediate graph. And I'm not going to bother drawing the points like I did before. Well, I kind of will, but I'll do it faster. So I want to first translate it to the left by 1 unit. So this line is going to go, instead of here to here, it'll go right about here to here. This is not going to be my final graph, okay? This is just an intermediate graph. This line here is going to get translated to the left by 1 unit. So this point will be on the graph, this point will be on the graph. I'll get a line about like this. I'm purposely making it dashed because it's not the final answer. This little semicircle type of thing gets translated to the left by 1 unit. So it's going to look about like this. And then this part gets translated to the left by 1 unit. It's going to look about like this. So that's the graph of f of t plus 1, now multiplied by 2 to get the graph of h. So again, all the y coordinates need to get doubled. Let's use a different color here. So this line here where the outputs are at 1, those outputs will get doubled to 2. So I'll get a line right about like that. This value right here, when t is negative 2, is 0. 2 times 0 is 0. I still have to go through this point. That's going to be on the graph of the final function here, h of t. This point, second coordinate, gets doubled from -2 down to -4. 2 times -2 is -4. So I get a line going about like this here. Something about like that. And then these points have their second coordinates doubled. This one gets doubled again to -4. This one, where the local max is, has a max value of -1. It gets doubled to -2. So you get no longer a semicircle type thing, but more like a parabola. It's not really a parabola, but it looks parabolic. It's skinnier, you might say. Actually, I did make this thing to be a semicircle. The scales are off on these axes a little bit, so it doesn't look exactly like a semicircle. And then, again, the second coordinate of this point is 0, so 2 times 0 is 0. You got to go back up there. So that's the graph of h of t equals 2 times f of t plus 1. That's the final answer. All right, third part, part C. J of t is negative f of t, then plus 1. Do the negative f of t first. By the way, if you had done the transformations in the opposite order for b, you would have gotten the same answer. You could have stretched vertically first and then translated to the left. With this one, you have to do it in the order that you see. You have to apply the negative f of t first and then add 1, because if you did it in the opposite order, add 1, then do the negative f of t, you'd actually have a minus sign there, because the minus sign would get distributed through the parentheses, essentially. So we have to think about the transformation of what happens when you take f of t and put a negative sign in front of it. That reflects the graph across the horizontal axis, because all the second coordinates get negated. Any positive outputs become negative outputs. Any negative outputs become positive outputs. And then adding 1 is going to add 1 to those outputs. So it's going to be a vertical translation upward by 1 unit. So once again, we'll have an intermediate graph representing first the reflection across the t-axis. So I need to take all the y-coordinates and negate them. So the y-coordinate of -1 there becomes a y-coordinate of positive 1 there becomes a y-coordinate of -1 here. These positive values become negative values. These negative values become positive values. We need to go from a value of -2 up to +2 here, about like that. And then keep going here. Oops, got the wrong scale there, sorry. More like that. And then this semicircle that's concave down will become one that's concave up over here. And then we got a line going down about like that. For the final answer, again, now we need to add 1 to that. Let's once again make it in red. So now we need to do a vertical translation up by 1 unit. So the final graph is going to look like this here. Go up by 1 unit. Looks like this part's going to go like that. Semicircle type of thing here. And then a line not all the way down to the t-axis. This is getting translated up by 1 unit. So we're going to end at the point 5, 1, it looks like right there. So this is going to be the graph of j of t. J of t equals negative f of t plus 1. Okay? So that's the idea of how to use transformations here. Why are transformations useful? We'll see that at the end when we think about how they help us understand the graphs of quadratic functions. The second problem is about function composition. We've got two functions, f of x equals x cubed and g of x equals 3x minus 1. We want to find various things. Take it step by step. Part A, find this expression. F, what's that? That's a circle, a composition operator if you want to be official about it. F circle G, or F compose G of 2. Some books don't use this notation. I like emphasizing that some mathematicians do use it, so you want to be aware of it. What does it mean? It means do F of G of 2. In other words, when you see this expression, work from inside out, evaluate G of 2 first. Whatever number you get, then gets plugged into F. Work from inside out. G is the inside function, F is the outside function. So let's go ahead and do that here. F circle G, or fog if you like, of 2. Not all books use that notation. It's a nice notation sometimes to use because it emphasizes that we are combining two functions to get a new function in a different kind of way than arithmetic, for example. It's sort of this, like a symbol, like a plus sign or a times multiplication sign, things like that. So what's G of 2? Evaluate that first. Plug 2 into G. 3 times 2 is 6, minus 1 is 5. g of 2 is 5. So we need to now find f of 5. Plug 5 into f. I need to do 5 cubed. 5 cubed is 125. So that's the answer to part A. Let's use a different color for part B. Part B, find g compose f of 2. G of f of 2. So now we switch the roles of f and g. F is now the inside function, g is the outside function. Do you get the same thing? Is function composition commutative? In general, it's not. Let's see what happens here. So first, I have to work from inside out. What is f of 2? I need to find 2 cubed. 2 cubed is 8. So I need to evaluate g of 8. There's no reason a priori that we should get the same answer as we did in part A. And in fact, we do get a different answer. Plug in x equals 8 here. 3 times 8 is 24. Minus 1 is 23. These are not the same. That's a not equal sign, a sideways not equal sign. In general, function composition is not commutative. If you switch the order of the functions in the function composition, you will not get the same function. Now, there are some certain special and important cases where that does happen, but not here. Part C. C and D are essentially the same thing, except we're doing it at a general value of x. F compose g of x is f of g of x. This typically gets a little bit more confusing for students. You're plugging g of x into f of x. Sometimes functions are thought of as machines. It's like you've got the g function that's getting done first here. This is a bad picture of a machine. The g function that gets done first, you plug an input, turn the crank, or push a button. Out comes an output g of x. And then that gets plugged into f. The f function is down here. And you get an output f of g of x. You need to take the formula for g and plug it into f. The formula for g, to how to find the output at a general input x, is 3x minus 1. Now here's the most confusing step. You're not doing the multiplication here. This is not f times 3x minus 1. F is a function. It's not a number. It's f of 3x minus 1. You need to take the entire expression and treat it like the x in this formula up here. So that entire expression, 3x minus 1, needs to get cubed. Now, if your teacher doesn't care about you simplifying this, you could stop there, okay? But maybe your teacher wants you to expand it, and you should be able to. There is something called the binomial theorem that allows you to expand this fairly rapidly, even if it were 4th or 5th or 6th power there. But just in case you don't know the binomial theorem, let's go ahead and do the actual multiplication here. Multiplying 3x minus 1 by itself with 3 factors here. So let's multiply those two first. FOIL, right? F-O-I-L. First times first. 3x times 3x is 9x squared. Outside times outside and inside times inside are both negative 3x. So that'll give me a negative 6x. Last times last is negative 1 times negative 1 is positive 1. Now do this multiplication of a trinomial times a binomial. I would take this thing here, 9x squared, and multiply it times each term, then go to the negative 6x and multiply it times each term, and then go to the 1 and multiply it times each term. This is all justified with the distributive property. 9x squared times 3x is 27x cubed. 9x squared times negative 1 is minus 9x squared. Negative 6x times 3x is negative 18x squared. I'll put that down here. Line up like powers here. Negative 6 times x times negative 1 is positive 6x. Hopefully I don't make a mistake. Double checking my work here. And then do it with the 1. 1 times 3x is 3x. 1 times negative 1 is negative 1. Now combine the like terms. 27x cubed minus 27x squared plus 9x minus 1. If there's a mistake, I'll make a note about it in the video. I think that's right. Don't think I made a mistake. All right. On to part D. Do the same kind of thing in the opposite order. This one is a little quicker. Okay. Do g compose f of x, which by definition is g of f of x. Now f of x is the inside function, gets done first, then g of x is the outside. I'd switch around the f and g machines. The formula for f of x is x cubed. In the formula for g, I need to replace any x's with x cubed. Here's the formula for g. I need to replace that x with x cubed. And then you're done. There's nothing else you can do with that. So that's the formula for the other composition, and these are definitely not equal to each other in general, though they might be equal to each other at certain values of x. Part E, something completely different. F of x, g of x, what's that? That's just multiplication, right? You've got the outputs f of x and g of x, and they're just next to each other. That implicitly means multiply. We're multiplying the functions now, not composition. F of x times g of x. F of x is x cubed. G of x is 3x minus 1. That's the answer, but if we want to expand and simplify, we'd get 3x to the fourth minus x cubed. Okay? That's a composition problem. While number 2 was a problem about function composition, number 3 is a problem about function decomposition, doing the opposite thing, essentially. Number 3, in each case, determine functions f and g such that h of x equals f composed g of x equals f of g of x. Why in the world would you want to do this? It's actually really, really important. In fact, you might say decomposition is a more important skill than composition. It comes up all the time in calculus when we need to use something called the chain rule. Do not choose the simplest case, f of x equals x or g of x equals x, because then you're not really doing anything that's going to be helpful for the chain rule, for example. Part A, the function is h of x equals x squared plus 1 to the 100 power. Are you kidding? 100 power. Well, I'm not going to expand this, not even with the binomial theorem. But it is important to realize this can be thought of as a composition. And in calculus, you could differentiate it, find its derivative using the chain rule, and you don't have to expand it. G is playing the role of the inside function here, and f is playing the role of the outside. So when you think about plugging a number in for x, ask yourself what kind of operations get done first. Well, first you would square, then you'd add 1, then whatever number you get, you'd raise that to the 100 power. So there's really 3 operations going on, but it's probably simplest to think of the inner operations in the g of x with 2 operations, x squared plus 1. And then f of x is just raising to the 100 power. So f of x is x to the 100, and g of x is x squared plus 1. Did that really work? Is that really right? Go ahead and think about, like we did with number 2, what is f of g of x? That would be f of x squared plus 1. And what I told you in number 2 is when you see an expression like this, whatever's inside the parentheses, plug that expression into the formula for, in this case, f, wherever you see an x. So that entire expression, x squared plus 1, would get raised to the 100 power. It does equal h of x, okay? This is correct. G of x is the inner function. That gets done first, x squared plus 1. F of x is the outer function. So a little confusing, maybe just partially because you're using the variable x all the time, and it just gets confusing. Because that you could use different letters for the variables. You could call this f of u is u to the 100 if you preferred. Maybe that would make it a little easier. That's allowed as well. But the directions do say f and g, and they do emphasize that they're functions of x. So we'll go ahead and do that here. Part B, h of x equals the square root of x squared plus 1. Once again, x squared plus 1 is the function that gets done first, before now square rooting. So the inner function g of x is still x squared plus 1. The outer function f of x is no longer x to the 100, it's the square root of x. Or x to the 1/2 if you prefer. Inner function is still the same, x squared plus 1. Okay, and I'll let you check that. Part C, h of x equals e to the negative 3x power. What operation gets done first? That's the g of x, the inner function. Take the number x and multiply it by negative 3. That's the g of x. G of x is negative 3x. What's the f of x? What other function is here? It's e to a power. e to the x. F of g of x is f of negative 3x. In the formula for f, replace x with negative 3x. You're going to get that function h. Okay? That's the answer for part C, and yes, this was the answer for part B. Number 4 is a problem about function composition in an applied setting. A spherical balloon is growing, getting bigger over time. Its radius r is a function of time. R equals 2t plus 3 centimeters when t is in seconds. Okay? Now, there's no function notation used here. Don't let that throw you. I could give this function a name. I could call it, well, how about g of t? Or f of t if you prefer. It doesn't matter. Okay? Even though no function notation is used, you certainly can use function notation if you want. Part A. Find the volume of the balloon as a function of time. I've got the radius as a function of time. What about the volume? Well, it's a sphere, right? It's a spherical balloon. We know the volume of a sphere is 4/3 pi r cubed. That's how the volume of a sphere depends on the radius. Now, I'm not using a function notation there either, but I could. I could call this f of r. And unlike number 3, where we used x for independent variable all the time, here we are using different independent variables, t for this function and r for this function, because they have real-life meanings that are different. T is time in seconds, and r is a radius in centimeters. Okay, so it's a good thing in this case to use different letters for those variables. That's how the volume depends on the radius. We want the volume as a function of time. So now we need to use the fact that the radius depends on time. Replace r with what it equals, g of t. And what is g of t? It's 2t plus 3. Okay? And once again, like in, what was it, problem 2, we could expand this with the binomial theorem or actually expand it to write it as a big long expression. In fact, I'm not going to bother this time. I'm just going to say that's the answer. In fact, this form of the function is simpler for the purposes of calculus. It's simpler in terms of finding the derivative using the chain rule and that kind of thing. So I'm just going to leave it like that. We did ultimately find here f of g of t. This is ultimately f of g of t, f compose g of t. Don't let it bother you that we used a different letter for the independent variable of f. Right here we used an r. Okay, this is still ultimately, when I do the composition, a function of t. So that's how the volume depends on time. Part B says find the time as a function of the volume. What? Shouldn't the volume depend on time and not the other way around? I mean, time is the ultimate independent variable, right? Well, physically speaking, you might say it is, but mathematically, you certainly can find time as a function of volume in this case. You can reverse their roles. This formula is telling you, if you know how long has gone by, how to find the volume. In finding for time as a function of volume, it would say, if you know the volume, it would tell you what the time was. Okay, it would depend on the situation and what time is time 0, for example, in your setup if you're thinking about real life. The goal is just to solve this equation for t as a function of v. Isolate t. It's not as hard as it looks. We're ultimately going to have to take a cube root and then still more algebra after that. First, isolate the 2t plus 3 cubed on both sides, on one side, excuse me, by multiplying both sides by the reciprocal of this, dividing by it effectively. Multiply both sides by 3 over 4 pi. This is the same as 4 pi over 3. I can multiply both sides by 3 over 4 pi. And on this side, it'll get cancellation. And I'll just be left with 2t plus 3 quantity cubed. Now take the cube root of both sides. I'll switch the order of these things as well. 2t plus 3 is going to be the cube root of 3, I'll put the v up here, 3v over 4 pi. I could also write that as 3v over 4 pi to the 1/3 power if I preferred. Now just isolate t. Subtract 3 from both sides, and then divide both sides by 2. Careful that you write things correctly. For example, if I subtract 3 from both sides, I certainly do not put the 3 under the cube root. I put it over here. It's separate from the cube root. You do the cube root first and then subtract 3. Divide both sides by 2. T is going to be 1/2 of this. 1/2 times the cube root of 3v over 4 pi minus, I also have to divide the 3 by 2 to get minus 3/2 right there. That's time as a function of volume. Should I give these functions names? I mean, I called this one up here f of g of t. I could also call it h of t. So ultimately here, v equals h of t equals this thing here. If I give that a function a name h, it's traditional to call this h inverse and to write it like this. That does not mean -1 power. It does not mean -1 power, because if you're going to raise h of t to the -1 power, you just do 1 over this entire thing, which is different than this. Very different. So this is not a -1 power, but it is standard notation for inverse functions. What's the independent variable of h? It's not t. It's v. But wait a minute. Didn't your teacher tell you when you find inverse functions to swap the variables? Yeah, you can do that, and it's a good idea in some circumstances when your variables don't mean anything, when they're just arbitrary variables that don't have any real-life meaning. And so that when you graph both graphs on the same set of axes with the x-axis, say, horizontal, that you get the reflection property across the line y equals x. But if your variables mean something, time and volume in this case, do not switch them. That'll just confuse the issue. This is fine. That's the inverse function, okay? This is the formula you'd use to find the time that's gone by when you know the volume. Leave the variables as they are because they have a real-life meaning. Number 5 is a really important kind of problem to get good at for calculus. It comes up a lot with derivatives. Suppose f of x equals x squared. Our goal is to fully simplify the expression that you see here, the fraction f of x plus h minus f of x, all divided by h. And to fully simplify it, we need to assume h is non-zero, though in calculus what ends up happening is you still think about what happens to this expression as h gets really close to 0 without equaling 0. It's called a limit. All right, so what do? Take a breath. People make mistakes in this. You got to get practice. F of x plus h. What is that? I've been talking about this in recent problems here. X plus h, that entire expression gets plugged into the formula for f in place of the x. Not a multiplication. This is not f of x times h. F is not a number. It's a function. It's f of x plus h. Replace x with x plus h, and you'll get x plus h quantity squared. Subtract f of x from that. F of x is just x squared. All divided by h. We want to fully simplify this. That's not fully simplified. We need to expand. And somehow this h not being equal to 0 must be important. Well, I don't want to divide by 0. H can't be 0. So expand this. FOIL it. You'll get x, if you want to write it down, x plus h times x plus h. First times first is x times x is x squared. Outside times outside and inside times inside are both x times h. So you get, I'll write it as 2hx, or 2xh, it doesn't matter. And then last times last is h squared. Don't forget about subtracting the x squared. And something kind of magical happens. The x squareds cancel. And with what's left on top, an h can be factored out, like this. And now it is important to say h is non-zero. I am not dividing by 0 here. If I divide the h out, h divided by h is 1. I get 1 times this, which is just that, which is just 2x plus h. That is an expression that equals our original one as long as h is non-zero. The original one is undefined when h is 0, but this is defined when h is 0. That's okay. That's still the answer. We still have equality here because we're assuming h is non-zero. As far as calculus and limits goes, the limit of this expression as h goes to 0 without actually equaling 0 is the same as the limit of this expression as h goes to 0. And as h goes to 0, we're not dividing by 0. If we plug in h equals 0, this does go to 2x plus 0, or just 2x, as h goes to 0. And that is enough to say the derivative of x squared is 2x. It's a little secret. Okay, we aren't two derivatives yet, but I wanted to just let you in on that little secret. So this is a pretty important kind of problem for calculus. Our last problem is a multi-part problem about a quadratic function. We will have to complete the square as part of what we're doing here, so that's good to practice. We're ultimately going to want to graph the function and find an inverse when we restrict the domain, which is necessary, it turns out. F of x is this quadratic function, x squared minus 6x plus 5. Part A, find the y-intercept of f. That's the easiest thing to do. The y-intercept is the value of y where the graph crosses the y-axis. It's the value of the function when x equals 0. Plug in x equals 0 into the formula for f. You'll get 0 squared minus 6 times 0 plus 5 is 5. The y-coordinate of 5 is where the graph crosses the y-axis. Part B, find the x-intercepts of f, also called the roots of the function f, also called the zeros of the function f, but I didn't want to overdo it here. Do this in two ways, both by factoring and with the quadratic formula. Now, factoring with quadratics is technically always possible, though if your roots are irrational numbers or complex numbers, it can be pretty tricky. And if they're rational numbers, it can still be tricky as well, though doable. I do want to give examples that are doable here, whose roots are integers, which are plus or minus 0, plus or minus 1, plus or minus 2, etc. And in this case, yeah, if you spend some time thinking about trying to write this as a product, x plus or minus something times x plus or minus something, the fact that you got a plus sign there and a minus sign there means we're going to need minus signs in both spots so that when we multiply last times last, we get a positive quantity, and the inside and outside terms still give you a negative quantity here. And a bit of experimentation reveals x minus 5 and x minus 1 work as a factorization. And this means your roots are 5 and 1, or I'll switch the order, 1 and 5. Those are your x-intercepts. Okay, and that's how to find it by factoring. What about the quadratic formula? There's a video I made recently where I sang the quadratic formula. I will not sing the quadratic formula here. It's one of my calculus lessons, I believe lesson 1.3. Anyway, if you want to hear me sing, go up here. This is in the form ax squared plus bx plus c. When a is 1, that's the coefficient of x. B is negative 6 and c is 5. So it's negative b. Now b is already negative 6, so negative b is positive 6 plus or minus the square root. Negative 6 squared is positive 36 minus 4 times 1 times 5, 4ac, all over 2a, which is 2 times 1. So this gives 6 over 2 is 3, plus or minus, looks like we're going to get a square root of 16 up there, all over 2. Square root of 16 is 4. 4 over 2 is 2, so we get 3 plus or minus 2. And 3 minus 2 is 1, and 3 plus 2 is 5. We do get the same answers. That's good. Part C, complete the square to find the vertex of the graph and confirm the roots this way as well. And then graph f. Part C has got 3 parts to it. Complete the square. What does that mean? So we have x squared minus 6x plus 5. I talk about in my lesson video how this is related to actual squares, geometric squares. There are plenty of videos that explain that. I don't have the time for that. Here's just the method. When the coefficient of x squared is 1, which it is here, that's the easiest situation. Take the coefficient of x, which is negative 6 in this case, divide it by 2. Negative 6 divided by 2 is negative 3. square that number, square, find a square whose sides or whose area is -3 squared is the reason we call it squaring. -3 squared is +9, and add that number to this expression. And then you say, well, wait a minute, you can't just do that. Can you? Is that allowed? Well, it's allowed as long as you subtract it off as well. But then why in the world would we do that? The reason is because, almost like magic, this expression here becomes a perfect square. And in fact, if you think about it carefully, you can factor it as x minus 3 quantity squared, that expression that's in the parentheses. That's the magic of completing the square. Taking that coefficient, when this coefficient is 1, taking that coefficient, -6, dividing it by 2, and then squaring that number, adding it in there, subtract it off to compensate. This part right here will be a perfect square. It's really cool. Don't forget to simplify this part. 5 minus 9 is -4, so we get a -4 there. That is what we get when we complete the square. We want to use this to find the vertex of the graph of f. The vertex is going to have coordinates 3, the first coordinate making this 0, -4. Because this is called the vertex form, vertex is going to be 3, -4. Why is that going to be the vertex? Well, I'm kind of skipping ahead here. It's really essentially to part D and thinking about the graph at the same time here. The graph of a quadratic function is called a parabola. There's a technical meaning of the word parabola, but it basically looks like this or like this. We won't get into the technical meaning. If the coefficient of x squared is positive, as it is here, it's looking like this. It's concave up, looks like a smile. And the vertex is the low point, the lowest point in the graph. Why are these the coordinates of the vertex? Because this function, as a function of x, will be as small as possible when x is 3, right? There's any other value of x, we're not considering complex numbers at all. Any other real value of x will give you an output of this part of the function right there that's not negative. It's greater than or equal to 0. And then if I subtract 4, the outputs are always bigger than or equal to -4. It's as small as possible when x is 3. And its value when x is 3 is -4. That's got to be the low point in the graph. And that's doing part D. It's going to be a minimum point, a low point in the graph. So I'm doing parts C and D at the same time here. Anyway, so that's the vertex. Let's confirm the roots. If I set this equal to 0, to confirm the roots, the way you confirm the roots here is you add 4 to both sides and then take plus or minus square roots of both sides, and you only have to put the plus or minus on the right. Plus or minus 2, and then add 3 to both sides, and you get x is 1 or 5 again. Okay, you get 3 plus or minus 2, just like we did up here. Then graph f is the graph concave up, concave down. What does that mean about the vertex? Looking ahead to part D. Sort of doing part D at the same time here. The graph of f, using all the information that we have, the y-intercept is 5, so here's 5. X-intercepts at 1 and 5. 1 right there, 5 right here, say. Vertex at the point 3, -4. Here's 3. Here's -4 down here. These points are on the graph. And yeah, the graph looks about like this. Try to make it smooth. Lots of people aren't careful when they make parabolas. They make this too pointy here. I know it's not easy, and I'm not doing the greatest job either, but try to make it as smooth as you can. Okay, there's the graph. It is concave up, concave up. Concave up means it looks like a smile, it holds water. Technically speaking, the slopes are increasing is what that means. And the vertex is a minimum. A little bit more technically speaking, the output of -4 is a minimum value. It occurs when x equals 3. Okay? Part E, describe how to obtain the graph of f using transformations. I'm just going to describe that verbally without writing things down because I'm running low on paper. Thinking about the vertex form helps you think about transformations. That's similar to the very first problem we did in this video. If you think of g of x as being just the x squared function. We obtain f of x by first replacing x by x minus 3. That translates the graph of g to the right by 3 units. And then subtracting 4 from it translates it down by 4 units. So it's the combination of two translations. First to the right by 3 units, then downward by 4 units is how to describe this in terms of transformations. Let's combine f and g to finish off the video here. Is f invertible? Why or why not? If f is not invertible, explain why it is possible to restrict the domain, and choose one such domain and find the inverse function in that case. It sounds like a lot to do. Okay, first of all, is f invertible? No, it's not. Why not? It fails the horizontal line test. There are horizontal lines that go through the graph more than once. What does this mean? It means for any given output except for one of them, -4, there are 2 inputs. And for the inverse function to exist, you only want there to be one input that gives you that given output. So it's not invertible. If not, that's the answer, it's not. Explain why it is possible to restrict the domain. Say, I don't want the domain to be all real numbers, I want it to be something smaller. To make it invertible. Yeah, there are infinitely many choices for how to restrict the domain. To make it invertible, to make it pass the horizontal line test, so no horizontal line goes through it more than once. The two most natural choices are when x is greater than or equal to 3, or when x is less than or equal to 3. You might say x is greater than or equal to 3 is the most natural choice, but just for the sake of throwing a wrench in things and doing something somewhat unnatural here, let's do the less natural choice. For example, if I let the domain, I'll call it D, be the set of all numbers less than or equal to 3. I could use interval notation for that, or I could use set building notation. The set of all x such that x is less than or equal to 3 is one such domain where the graph passes the horizontal line test. I'm only focused on this piece of the graph over here. Passes the horizontal line test, no horizontal line goes through it more than once. I'm ignoring the other piece of the graph. How do you find the inverse function in that case? Use the squared formula here. I'm going to go ahead and write y equals f of x equals x minus 3 squared minus 4. You just solve for x as a function of y. Do you need to swap the x and y? That's actually up to you. Though if you want to graph it in the same picture with x being the independent variable in both cases, so you see the reflection property across y equals x, then you'd want to swap the variables. So solve for x. Add 4 to both sides. I'll write x minus 3 quantity squared equals y plus 4. Take the square root of both sides, and, okay, careful. Do I take plus or minus square root or both? You got to take one, because you want a single output for the inverse function. Which one do you take? Since you're wanting x to be less than or equal to 3 here, we better choose the minus square root. Because now when I finally add 3 to both sides, I get x equals, I'll go ahead and write it, f inverse of y equals positive 3. I added 3 to both sides. Positive 3 minus square root of y plus 4. I need to choose the minus square root so I get a function whose outputs are always less than or equal to 3. The restricted domain of f becomes the range of f inverse. They swap around. This is fine. You do not have to swap the x and the y. Okay, it's not necessary. Is it wrong to swap them? No, that's not wrong either. I could swap. I could write y equals f inverse of x. I mean, letters are they're just arbitrary symbols. It doesn't matter what they are as long as you're consistent. These are both correct answers. Use the swapped version if you go back to trying to graph the inverse function and graph it as the reflection of the original graph across y equals x, which would be kind of tricky to draw. Could I do it? I'm afraid I'm going to make a mistake. Yeah, it's tricky. Something like this, maybe. I'm making a mistake, I think, already. Something like that, I think, is the inverse function, okay? If you swap the variables and use x as the independent variable in both cases. Thanks for watching.